Yeah. So I'm going to
okay. So I should not touch this.
No, yeah. Yeah. Yeah.
Oh, okay. Uh, Good morning, my dear students. We are on again to Chemistry 102. I am Professor Ajayi, as you know, so I'm taking you on the identification of organic compounds. Organic compounds, either synthetic or natural products. For you to identify it, there are few steps involved. Okay. Number one is isolation and purification. Qualitative, number two is qualitative analysis, and number three is quantitative analysis. So let's go to isolation and purification first. Organic compounds are always found as mixtures, either synthetic or isolated ones from nature. Okay. At least one of the technique listed above, or below, is used for this purpose. As you know, simple distillation, fractional distillation. You also know one you may not really be familiar with now is steam distillation. But let's go to simple distillation first. Simple distillation is used to separate liquids with boiling points that are far apart, such as, for example, water. The boiling point of water is 100 degrees Celsius, and ethanol. Ethanol is 78. So if you have a mixture of water and ethanol, you can use simple distillation because of the wide difference in their boiling point to separate the two liquid. Simple distillation will also be used to separate liquid from solid. So that is that. Number two is fractional distillation. This is used to separate liquids with boiling points that are so close to one another. For example, if you have methanol is about boiling point 64, and even ethanol that is 78. You can see that they are so close. So for this, you can use fractional distillation. Number three is steam distillation. Yes, this one, like I said, you may not be aware of it before, but now steam distillation is used to separate volatile liquid or solid organic compounds that are immiscible or insoluble in water. When you hear immiscible, you mean a liquid that is not soluble in another liquid. So we use the word immiscible. So this technique is not applicable to compounds that react with water. So if you have compounds that react with water, then you don't use steam distillation. Why? Because you will have problem there. Also, you don't use this technique is not applicable to compounds that are decomposed on prolonged contact with steam or hot water with very low pressure at 100 degrees Celsius. So this technique can only be used for the stated type of compounds. And also the technique can help you. You can use it to calculate the vapor pressure or the molecular mass of a compound that is steam distilled. If the mass composition of the compound and water is known according to the equation that we have below. Okay, this equation is very, very important. MA over M water is equal to PA multiplied by MA over P water times M water. Now, let's define all these parameters. MA is the mass of the organic compound, okay, that you want to steam distill. PA is the vapor pressure of the organic compound, while MA, capital MA, is the molar mass of the organic compound. M water, small m water, is mass of water, while capital P water is vapor pressure of water. Then capital M water is molar mass of water. Now, for example, let's go through this simple calculation of steam distillation. For example, an insoluble organic compound A was steam distilled. The atmospheric pressure was 760 millimeter mercury. And of the 69 centimeter cube of the distillate, 60 centimeter cube was water. So the mixture boiled at which the mixture boiled when the vapor pressure of water was 740 millimeter mercury. If the density of A was 1.22 gram per centimeter cube, then we have to calculate the molecular mass of A. Now, solution. Of course, we said Ma is the mass of the organic compound. Therefore, in this question, we don't have the mass, but we have the density of the organic compound, and we also have the volume of the organic compound. And you know that the mass is equal to density times volume. So the density of the organic compound, 1.22 gram per centimeter cube, multiplied by 69 minus 60. Okay, 69 minus 60, because if you look above in the question, 69 centimeter cube of the distillate, out of the 69 centimeter cube of the distillate, 60 was water. So the mass of the distillate will be 69 minus 60. And we have 9 centimeter cube. So if you multiply it with 1.22 gram per cm cube, you have 10.98 gram. That's the mass of the organic compound, okay, of interest. And the vapor pressure of the organic compound can also be obtained. That would be total vapor pressure of water was 740. And you know the normal atmospheric pressure was 760. So just minus 740 from 760, then you have the vapor pressure of the organic compound. There it is, you can see it is 20 millimeter mercury. Now, our interest is to calculate the mass of the organic compound. Now we have mass of water, which is density of water times the volume of the okay, of the distillate. And from this, you can calculate, of course, the molecular mass of water is 18 grams per mole. So if you substitute all this, making mass of organic compound A, the subject of the formula, we arrive at 121.89 gram per mole. We are asked to calculate the molecular weight, and therefore we have done that. So the molecular mass of the compound, our organic compound, is 121.89 gram per mole. So what are other separation techniques that you also need to know to separate or identify an organic compound? Recrystallization, which is used to separate an insoluble solid from a soluble solid. That is recrystallization. We also have fractional crystallization, which is used to separate mixtures of solids of different solubilities at different temperature. We also have filtration, centrifugation, and we also have chromatography. I know you are all familiar with this, but I will talk a little. Maybe we should just define what chromatography is. We use chromatography to separate compounds based on their affinity between a mobile phase and a stationary phase. Okay, so for a chromatography, there must always be a mobile phase and a stationary phase for you to be able to separate the compounds effectively. We also have sublimation, we have evaporation. I need not to go or dwell into that. We also have decantation. Okay, we are all familiar with this, but let's go to solvent extraction, which is one I think you may not be too familiar with. What is solvent extraction, or what does we mean by solvent extraction? So it's a technique that is known also as solvent-solvent partitioning. Solvent-solvent partitioning, or liquid-liquid partitioning, where the redistribution of solutes between two immiscible liquids is involved. That is, we have two liquids that are not miscible together. So you can't use water and ethanol because they are miscible. So you use two immiscible, for solvent extraction, you use two immiscible liquid, okay, that are not miscible, and then you dissolve where your compound of interest is soluble in one and possibly insoluble in the other one. And partition coefficient, which is K subscript D, is expressed as the concentration in gram per dm cube of A in X, okay, that is in solvent X, over concentration in gram per dm cube of the same A in solvent Y. So we have two solvents. So that is solvent 1 is X, solvent 2 is Y. Also, like we did, let's try to solve a problem on solvent extraction. For example, 200 centimeter cube of water containing 20 grams of an organic compound X was extracted with 80 centimeter cube of ether. No, ether and water are immiscible, and the partition coefficient of X between ether and water is 10. We are then asked to calculate the mass of X that is extracted by ether in we normally do this in batches. It's either you have one batch, that is, you dissolve, you use the whole volume of your solvent at once, or in two batches. So in this problem, we are going to solve, we are going to calculate the mass of X extracted by ether in one batch, that is, using the whole 80 centimeter cube of ether, or in two batches of equal volume, that is, we divide the whole 80 centimeter cube of ether into two. So we use 40-40, that means in two batches. Now, let's see what the result will be. So solving for the first one, that is in one batch, let the mass of X transferred to ether layer be A. So let's use A to mean the amount of X that is transferred to ether layer in grams. Of course, if A is subtracted from 20, then that will give us the mass of X that is left in water. Okay, now let's apply our formula, our solvent extraction formula, which is partition coefficient Kg is equal to concentration in gram per dm cube over of X in ether over concentration in gram per dm cube of X in water. Now, we said we are going to, in one batch, we want to use the whole 80 centimeter cube of ether, which is equal to, which we have A, we extract 8 grams. So, the next line, therefore, 1000 cm cube of ether will be equal to A over 80, that is our the total amount of ether given to us. So A over 80 times 1000, and that will give us 12.5 A gram per dm cube. So that is the concentration of X in ether in gram per dm cube. So let's now look at concentration in water. So we are given 200 centimeter cube of water, and that's and the mass of the compound in the 200 cm cube of water will be what? 20 minus A. You know, up in ether we have 8 grams. Okay, so in 200 cm cube of water we will have 20 minus A gram. Therefore, just like we did for ether, 1000 cm cube of water will mean 20 minus A over 200, which is the volume of water given, times 100, times 1000, which gives, if you do that calculation, you see 5 into 20 minus A as, gram per dm cube. Now, our partition coefficient given, that is between, if you go back in that question, between ether and water is 10. Between ether and water is 10. If it is between water and ether, it will be 1 over 10. Okay, so let us be aware or to take note of that. No, partition coefficient Kg of X between ether and water is 10. Okay, but if it is between water and ether, then it will be the reciprocal of that. That is 1 over 10. Now, let's go back to our calculation. Now, Kd, we know our formula. Now, let's substitute the Kd and the concentration in gram per dm cube of X in ether over the concentration in gram per dm cube of X in water. So if you look at it, we have 10 is equal to 12.5 A over 5 into 20 minus A. If you do your calculation, do your cross multiplication there, you have 12.5 A. 12.5 A is equal to 50 into 20 minus A. And if you do this is simple arithmetic or simple maths, our A here, you see, is 16 grams. That is, in one batch, if we use the whole ether, the whole volume of ether at once, which is 80, the amount of the amount of X that we extracted out of the 20 grams is 16 grams. 16 grams. So now let's look at the calculation for in 2 batches. Okay, 2 batches, I told us earlier that we will divide the total volume of ether given to us by 2, because we are told we are to use or we are to calculate the amount of X extracted using in 2 batches of equal volume. So you have 40 there. Now, Now, also let's do the same calculation that we did. Same calculation. We say let the mass of X transferred to ether layer be A, and then the mass of X left in water will also be 20 minus A grams. Now, let's use the first volume, which is 40 centimeter cube of ether. So if 40 centimeter cube of ether contain 8 grams, okay, then 1000 cm cube of ether will be equal to A over 40 times 1000, giving us 25A gram per dm cube. Now, let's go to water. 200 centimeter cube of water also contains 20 minus A. So we assume that after we have removed A from 20, from A that is in an ether, then in water we expect to have 20 minus A. So the same way, 1000 centimeter cube of water will give 20 minus A over 200 times 1000, giving us 5 into 20 minus A gram per dm cube. Now, after these preliminary steps, let's now let's now substitute all these values into our KD. Our formula, KD is equal to concentration in gram per dm cube of X in ether over concentration in gram per dm cube of X in water. So when we do this, you see that the amount extracted in 40 centimeter cube of ether is 13.33 grams. Wow, that's in first batch. So let's now go to second batch. So when we now use the second 40, we divided our volume of ether into 2. We have used the first 40 centimeter cube of ether, and it has extracted 13.33 grams. Now, let's do the second extraction with what is left. So, second batch, the mass of X left in water after the first batch, of course, will be 20 minus our A, the one extracted in the first 40 ml of ether, and that is 20 minus 13.33 gram, which remains 6.67 gram in the mixture. Now, let the mass of the same way we do we did for the first batch, we are going to do here again. Now, let the mass of X transfer to ether layer also be A grams. And the mass of X left in water this time will be 6.67 minus A grams. Now, the second 40 centimeter cube of ether contains 8 grams, and we do the calculation again. 1000 cm cube of ether will give us A over 40 times 1000 is equal to 25 A gram per dm cube. That is for ether. And for water, we have 200 centimeter cube of water containing 6.67 minus 8 grams. Therefore, converting that to 1000 cm cube of water, we will have 6.67 minus A over 200 times 1000. And that gives 5 into 6.67 minus A gram per dm cube. Substituting this in our coefficient partitioning formula, still using our KD, which is still 10, we have 10 is equal to 25A over 5 into 6.67 minus A. And if you do your calculation, we see that we have extracted more. A now, we have 4.45 grams. Now, let's see the beauty of extracting our compound in 2 batches other than in 1 batch. So the total, you can see the total mass of X extracted in 2 batches, therefore, is equal to 13.33 plus 4.45, giving us 17.78 gram. You can see that this is higher than what we have in 1 batch. In 1 batch, we are able to extract only 16 grams, but in 2 batches, we have removed out of 20 grams that we have been able to extract 17.78 grams. So in conclusion, it means extraction in batches is better than in one batch. Okay, can I just pause here and take some feedback? If there are feedback. Okay, feedback. How do we get, okay, some question here. How do we get the slides for this course? Yes, do not worry. I will send, we will send the slides to you. Do not worry. The slide will make made available for us. Okay. What other thing? Okay. Let me still see more feedback. More feedback. Okay. All right. Maybe I should go on. Now, let's now go to the second part of identifying organic compounds. One of the things also is qualitative analysis. Qualitative analysis. This analysis is about what elements are present in a compound. So we can say it's an elemental analysis. Since most organic compounds contain carbon and hydrogen, then it is only necessary to test for others like nitrogen, sulfur, and the halogens, which and this is done using the sodium fusion test. In fact, it is called the Lassane sodium fusion test. How is this test carried out qualitatively? Now, a little bit of the organic compound, together with a small pellet of sodium, is introduced into an ignition tube and then heated gently. That is, your organic compound is introduced into an ignition tube with a small pellet of sodium. Okay, the mixture is heated gently at first and then more strongly to red hot. Now, the tube, while still hot, is pushed carefully in a mortar, mortar lab, so with a little distilled water in it. Now, the solution of this solution is filtered to get rid of the broken glasses. Since you crush the tube in the mortar, therefore it is expected that there will be some broken glasses in there. Now, after you have filtered this, okay, then you can take your filtrates, okay, take your residue and carry this test. You can test for nitrogen. You can test for nitrogen, okay, because that Lassane sodium fusion test that we carry out will have converted the carbon and the nitrogen and the sodium into sodium cyanide. So this is what you have. That's the first equation. You introduce your organic compound with a little sodium and a little distilled water. The carbon and the nitrogen in there is converted to sodium cyanide. Now, you remember our qualitative analysis. Take about 0.5 cm cube of a cold saturated solution of iron 2 sulfate, sulfate 6 that has been boiled momentarily to ensure the presence of some iron 3 salt. Is added to the portion of the filtrate from sodium fusion experiment. Now, what do you have? The solution is boiled for about a minute. Then you cool it rapidly, and then you acidify by adding concentrated HCl, acid dropwise. Now, there is formation of a Prussian blue or a bluish green solution, which is with or without precipitate, and that indicates the presence of nitrogen. I said the formation of Prussian blue or bluish green solution with or without precipitate indicates the presence of nitrogen. And the equation for those reactions is simply as we have here. Like I told us the first time, the first equation was sodium plus carbon plus nitrogen. That is all the carbon and nitrogen in your organic compound was converted to sodium cyanide. Now the sodium cyanide now reacts with your iron 2 sulfate that you added to give you sodium ferrocyanide, okay, plus sodium sulfate. Okay, that's the second equation. Now, the last one is that the sodium ferrocyanide will now react with your iron 3 chloride to give sodium chloride plus our Prussian blue, which is sodium iron ferrocyanide, okay, which is a Prussian blue. So the presence of that Prussian blue is an indication that nitrogen was present in your organic sample, okay, or organic compound. Now, how do you test for sulfur? We have tested for nitrogen. How do we test for sulfur in our organic compound? Okay. Also, in our sodium test, any sulfur that is present in the organic compound will also react with sodium to form sodium sulfide. Will have reacted with sulfur will have reacted with sodium to form sodium sulfide. So also from our filtrate, take a portion, okay, from the sodium fusion test, take a portion, a little drop, maybe 0.5 cm cube again, and a few drops of acetic acid, okay, and thereafter a solution of lead acetate is added. Now, what will be the result? Formation of a black precipitate will indicate the presence of sulfur. The presence of black precipitate indicates the presence of sulfur. Now, the equations are as follows. We are familiar with, we are already have introduced ourselves to the first equation. Now, the second equation is the sodium sulfide will react with the lead sulfide to give us the black precipitate we talked about. Is that lead sulfide plus sodium acetate So our interest is the black precipitate, which indicates presence of sulfur. Now, to also test for the presence of halogens, it can be chlorine, can be bromine, or chloride or bromine. So still from our sodium lacene lacene sodium fusion test, our sodium also will react with any halogen that may be present in the organic compound and give sodium halide. Give us sodium halide. That is in that equation you see Na plus X is equal to NaX. where X can be chlorine, like I said, or bromine. Now, the filtrate, that is our sodium halide, just take from the filtrate, acidify it with nitric acid. The acidified solution is then boiled to eliminate any cyanide and sulfide which may be present in the solution to avoid any form of interference. Now, the solution is cooled and silver nitrate is added. Of course, this is the normal halide test. Now, the formation of a white precipitate, which is soluble in excess ammonium hydroxide, indicates the presence of chlorine, of course. And the formation of off-white or yellowish white precipitate, which is sparingly soluble in excess ammonium hydroxide, indicates the presence of bromine. Okay. Now, the formation of yellow precipitate, which is insoluble in excess ammonium hydroxide, will indicate the presence of iodine. So, take notes. If I were you, I will underline those very important differences between the test for chloride, the test for bromide, and the test to confirm iodine. Of course, the equation also is here. If it is chlorine, the sodium will combine with chlorine to form sodium chloride. And the sodium chloride solution, when you acidify it and add silver nitrate, you obtain a white precipitate. Okay. And if you want to confirm that it is actually chlorine or chloride, add to that precipitate, add excess ammonia. When you add excess ammonia, if that precipitate dissolves, that is, you have a silver ammonium solution, that is soluble complex salt, okay, AgNH3(2). Okay, so when the precipitate dissolves, then you are sure your compound of interest is chlorine. That is, chlorine is there. And the same thing, if you do the same thing for sodium bromide, you get an off-white precipitate. And for iodine, you have a yellow precipitate. Now, let's quickly run to the third part, which is quantitative analysis. Yes, quantitative analysis. This will involve, as you know, calculation. Now, what is quantitative analysis in identifying an organic compound? The analysis is about knowing the amount of each element present in a known mass of an organic compound. You know, in qualitative, we only determine, we only identify, or how do I put it now? We just look at what shows or whether chlorine is there, whether sulfur is there, whether nitrogen is there. Okay, but we want to know the amount. Then quantitative analysis is the ways to go. Now, the first quantitative analysis, the first way is to go through combustion. Number one is combustion. You subject the organic compound to combustion. That is, you burn it. This is to quantify carbon and hydrogen in a given mass of an organic compound. It is also used, that is, combustion is also used to determine the molecular formula of gaseous hydrocarbons. When a known volume of a gaseous hydrocarbon is packed in excess oxygen, then carbon is converted to carbon dioxide, and the hydrogen that is present in the organic compound is converted to steam. Of course, I know you know this. So after cooling and passing the gas produced over a weighted bottle containing potassium hydroxide solution, the gas left will be unreacted oxygen. Okay, and the molecular formula of the hydrocarbon can then be calculated using the following chemical equation. No, so let's assume, or let's make our organic compound to be CXHY. So thinking it is purely hydrocarbon. So we represent it as CXHY. Okay, this equation is fundamental, it's very important. So CXHY plus X plus Y over 4 oxygen, that is as the X plus Y over 4 is the mole of oxygen that will react with our organic compound, our hydrocarbon CXHY, to now give, we said this will be converted to carbon dioxide and water. So X mole of carbon dioxide is produced plus Y over 2 mole of H2O. Now let's look at an example to which we can subject we want to do a quantitative analysis of this question. It says 16 centimeter cube of a gaseous hydrocarbon was sparked or mixed with 90 cm cube of oxygen. Okay, after explosion and cooling, the volume was 66 centimeter cube. It was reduced to 34 centimeter cube of residual oxygen by absorption with potassium hydroxide solution. Then what is the molecular formula of the hydrocarbon? Now let's solve this together again. Let's pay attention. It can be very interesting if you get it. Now, let the molecular formula, let's assume the molecular formula of that hydrocarbon is CXHY. Okay, so applying our earlier equation given, it will be CXHY plus X plus Y over 4. I'm sorry, I think the X and Y should be lowercase, should be lowercase, but I will correct that in the note that I will send to you. Now, it is important that you bring out the various parameters and their quantity. So, from our question, the volume of the hydrocarbon that we want to identify, okay, how be it quantitatively, is 16 cm cube. 16 cm cube, that's the volume of the hydrocarbon. Then the volume of CO2 produced, will be 66 minus 34. It will be 66 minus 34 because when the gas produced was shaken with potassium hydroxide, we saw that the thing reduced. So that means the amount of carbon dioxide is 32. It's 32 cm cube. Then the volume of oxygen used, therefore, that is the volume of oxygen that reacted. Excess oxygen was used from that question. Okay, so the volume of oxygen used that reacted actually will be 90 minus 34, and you have 56 cm cube. Now, applying this, putting this, all these extra answers under our equation. So we have 16 centimeter cube of CXHY, and we have 56 centimeter cube of oxygen that reacted with 16 centimeter cube of hydrocarbon, that is CXHY, to give 32 centimeter cube of carbon dioxide. Now, by Gay-Lussac's, either Gay-Lussac's or even Avogadro, it says by Gay-Lussac's law, volume is related to mole, and therefore to obtain the simplest mole ratio, all we need to do is to divide by 16, because CXHY is 1 mole, which is 16 centimeter cube. Okay, so 1 mole of CXHY will react with 3.5 mole. That is, if you divide 56, okay, by 16, because we said we should divide what we have up here in volume with 16. So if you divide 56 above with for oxygen with 16, we have 3.5 mole of oxygen reacted to give 2 mole of carbon dioxide. I hope we are following. Now, the number of moles of carbon dioxide is 2. That is very clear. And the number of moles of oxygen used is 3.5. And therefore, if you can easily get that our X is equal to 2. That means our X, since we said XCO2 was produced, and that X is 2 moles. So that makes it easy. Now we know X now. Therefore, we know X now. We are only interested in Y. So just to calculate Y, substitute X is equal to 2 into X plus Y over 4. Okay, since the volume the volume for oxygen used is X plus Y over 4, which translates to 3.5. So substituting X is equal to 2, Y equals 6. And therefore, the molecular formula of our hydrocarbon is C2H6. C2H6. Since our X is 2, our Y is 6. So just substitute that in our CXHY. And therefore, we are able to completely solve the problem, which says we should calculate, or we should determine we are to determine the molecular formula of the hydrocarbon, and that is what we have just done. Now, example 2. Example 2. It says write balance equations for complete combustion in oxygen of the compounds. 1, an alkane. 2, an alkyne, each of which contain n number of carbons, atoms in their molecules. Then equal volumes of the 2 hydrocarbons were separately completely combusted in oxygen. The volume of steam produced in 1, that is with alkane, and 2 with alkyne, was in the ratio 2:1. Then we are to determine the value of N. Hence the formula for the alkane and the alkyne. We are also given hints there that all measurements were carried out at 120 degrees Celsius. Now, let's go straight to solve this. Of course, the general formula for an alkane is CnH2n plus 2, which we all know. And for an alkyne, which is a triple bonded hydrocarbon, okay, is CnH2n minus 2. And for the combustion of these 2 hydrocarbons with oxygen, it is also a standard. We have these 2 standard equation, which is a little bit different from what we use above in example 1. This one, the combustion reaction will give for alkane, we give CnH2n plus 2 plus 3n plus 1 over 2 oxygen, giving NCO2 as product plus N plus 1 H2O as product. Now, for the alkyne, the equation, the standard equation for the combustion of an alkyne, which is represented here in 2, CnH2n minus 2 plus 3n minus 1 over 2 O2, which we give NCO2 also plus N minus 1 H2O. Now, since we are to determine the value of N by which the molecular formula of the alkane and the alkyne will also be obtained, therefore, if you look at what we have here, and of course, we are given the ratio of the alkane to the alkyne, which is ratio 2 to 1. So we can easily use the mole ratio of their of the water produced, which is N plus 1 mole of water is produced for alkane. N minus 1 mole of water was produced in alkyne, and which is equal to ratio 2 to 1. So if you cross multiply, our N will come out, which is 3. And therefore, our molecular formula for alkane will be C3H8. C3H8. And then the molecular formula for the alkyne is C3H4. Isn't this interesting? Yes, it is. Okay, let me see whether I can still take Dumas method, or before that, can I also get some feedback? Okay. The slide, yes. We are still asking for the slide. That will be made available. Okay. Okay. Okay, somebody is asking, what's the topic that is being treated? Is okay, somebody has answered, is identification of organic compound, which deals with purification, isolation and purification. Answered your question? Yes. We have just finished dealing with combustion. Okay. I don't understand why we are subtracting for oxygen. Where? Okay. I will attend when we come for tutorial. We will attend to that question. Okay. Okay. All right. Let me go back. Now, we are still under quantitative analysis of organic compound. Now, let's look at another method number 2 of quantitative analysis of organic compound. And number 2 is Dumas method. Dumas method. This is used to quantify nitrogen in a given mass of an organic compound by direct measurement of nitrogen gas produced. Okay. Number 3 is the Jeddah method. Jeddah's method. This is also used to quantify nitrogen in a given mass of an organic compound. So both the Dumas and the Jeddah method they are used in quantifying nitrogen in a given mass of an organic compound. How? By converting nitrogen to ammonium sulfate. Then the ammonium sulfate that is obtained or generated is then heated with sodium hydroxide to produce ammonia. The ammonia produced is dissolved in a known volume of standard acid, and the ammonia is estimated, that is, the ammonia obtained or that is produced is estimated by back titration. And the following equation describe what the Jeddah method is about, okay, in determining the amount or quantifying the amount of nitrogen in an organic compound. So if you have an organic compound, if you add H2SO4 to it, it will convert the nitrogen to ammonium sulfate, solution. Now, the ammonium sulfate solution is sodium hydroxide is now added to that ammonium sulfate solution that is obtained. And then you obtain sodium sulfate, water, and ammonia gas. Okay, or I'm sorry, ammonia solution. Now, the ammonia solution is now back titrated with H2SO4. Okay, and we get the ammonium sulfate back. Now, can we, I don't know whether we can finish this. Let me see. Just we have less than 10 minutes. Okay, I think we are good to go. So let's solve this problem on Jeddah method. Let's solve this problem on Jeddah method. For example, if you have 0.53 gram of acetanilide, of course, acetanilide is an organic compound that contains carbon, hydrogen, oxygen, nitrogen. Okay. Now, 0.53 gram of acetanilide was subjected to Jeddah determination, and the ammonia produced was collected in 50 centimeter cube of 0.50 molar H2SO4 on dilution to 250. That's 50 mil. Okay, is now diluted to 250 cm cube. Then the acid was obtained, was titrated against 25 cm cube portion of 0.05 molar sodium carbonate solution. 13.60 cm cube of acid was then required for each titration. Now the question, what's the percentage of nitrogen in the acetanilide? Okay. What's the percentage of nitrogen in the acetanilide? Now, the ammonium, we already obtained ammonium. We have already converted the nitrogen into ammonium sulfate. Now we want to determine. Okay, so the first equation now is the ammonium sulfate is reacted with sodium carbonate solution. Sorry. Is reacted with sodium carbonate solution. And then we have, what do we have here? Okay. No, I think it's supposed to be okay. Sorry, I think I have a small issue here. Maybe I should just pause here. I think there is a little Okay, okay. There's a little problem with this question. Okay. Okay, let's just pause here and take some. Let me get the last feedback and possibly answer some questions. We'll come back to this possibly on Monday, God's willing. Now, okay, I want to try and take some questions. It's like that is the standard formula to get the most of CO2 H2O. Yes, yes, yes. Please help us with the slide. Yes, I've already said it. I will supply the slides to us. We get the slides. Okay, please, how did you get to? That is a standard formula. It's a standard formula. You are asking how I got the 3n plus 1 over 2 for oxygen. It's a standard formula for combustion of hydrocarbon, okay? Especially alkane, especially alkane, especially alkane. Okay, okay. What was happening? Yes, identification of organic compound. That's what we are treating. Yes, solvent extraction is a topic under identification of organic compound. Okay. Yes. Okay. Yes. I think this is a very good point to end the lecture today. We'll continue from here, God's willing, on Monday. And also let me inform us that our tutorial classes, CHM 104, tutorial classes commences next Monday. So check your WhatsApp platform and identify your group, and also let your class advisor contact the lecturer involved for your own tutorial, so that you can make arrangements for a suitable venue for the class. Thank you very much.
Good morning this morning. We're on again for physics 102. For those who are available last meeting, you can discover that we're able to go to some level of discussing Gauss' law. So remember, we went as far as this diagram where we explain the direction of the electric field, the area of the plate, and the angle it makes. And I told you this is important to define the charges around the electric field. Then may I remind you also that I also pointed out the importance of the shape of any object, which determines the quantity of charge on that shape. So I can ask you at any time that which of the following is correct about charges acting on the body. So you should be able to pick your correct answer from those factors given to you. So, course of our time, we would like to move to okay. I think this permittivity of free space was mentioned last meeting. Epsilon naught, which is 1/4 pi k e. And I told you that the equivalent value will be given to you in the exam, and you surely need it. So master that. I also reminded you last meeting that you can be tested on the unit of epsilon naught. So you need to take note of the unit itself. Coulomb square and Newton meter square. So if I can like and reverse it to test your knowledge, well, unit is important, and because it's connected with the free space of the permittivity theorem. So take note of that. And remember, K is equivalent to 1/4 pi epsilon naught. That can be substituted for at any point in time. Now to electric flux. The electric flux through the closed spherical surface that surround the charge Q can be expressed as this is phi of E, equivalent to 4 pi KEQ. So anytime I want the value of electric flux, you use this formula. And sometimes when the charge is only given the charge within a rod or the charge within a particular conductor, then it is easier for you to use epsilon naught to divide the actual value of charge given. So you don't need any other 4 pi, whatever. You just say flux is equal to Q over epsilon naught. That's the fastest way to get your answer if the charge is given. So, in other words, the provision of the variables determines what you have to use to solve problems. Because for physics generally, there are possible 2 or more equations to solve a simple question. And we have done that to make it easier and better for the student. And like I told you last meeting, the more the question, the happier you should become. And the more the equation, the more happier you should become. Because at your level, you should learn how to master that. Now, next slide. Electric field E produced by a charge Q at the location of a small test charge, Q naught, is defined as the electric force that's represented by F capital, exerted by Q, that's the total charge, on Q naught when divided by the test charge. We are still dealing with charges and its relationship with the field region and the material on which the charge is operating. So that will now lead you to the next equation. That is F over Q naught will be equals to E. And so what's going to be your unit for in that case? That's Newton per Coulomb. Let me remind you once again, you may be tested on units. So you must master all these units. And it's just that this class is no longer physical. Like I used to tell you in the normal physical class, I can come across you on the road, either at Nigeria or anywhere. Once I know you are taking this course, I ask you a question, you should be able to answer me correctly. And if you are able to answer that, you give me the number of your parents straight away. So mind you, this is where you are, that's why you are here. The next slide talks about electric field. Electric field lines are related to the electric field in any region of space in the following ways. Point one, that the electric field vector is tangential to the electric field line at each point. Then the electric field is large when field lines are close together and small when lines are far apart. Now, for those of you who want to check the past questions, this is one of the questions we have said before. But it's easier for any lecturer to turn the questions around. So the fact is what you need to be able to get it right. The next point, the number of lines per unit area through a surface perpendicular to the lines is proportional to the strength of the electric field in a given region. Now I need to explain this because there are principles behind lines of forces. So three variables have been considered since we started. Remember, we are talking about line of forces. We are talking about forces in nature. Then we're only talking about charges involved when forces are in different lines. Then we're also talking about the field, which is the electric field, within that line of charges. So these three variables are important for you to master. So this point will now bring the three together, that the number of lines per unit area through a surface perpendicular to the lines is proportional to the strength of the electric field in a given region. So the strength in that case talks about the value. So if the value is higher, the line of force is also higher. Don't forget that we have said line of forces is related by the inertia and the acceleration it experiences. That's why in the preliminary classes, you have been taught that force generally mass times acceleration. So take note of that. So anyone can now make use of the change of subject or formula you have been taught in mathematics. So meaning that the inertia on the line charge, which is represented by M, and M must be in kilogram. If you are given the value in gram, convert it to kilogram first in the exam or test. So M becomes what? F over A. And remember, I told you that when the motion of charge is within the gravity, your A is equivalent to G. So it's like now saying your mass or inertia is equivalent to F over G. And no G will be given to you in the exam because it's general value. The next point, the electric flux through any closed surface is equal to the net charge inside the surface when divided by the permittivity. So this leads you to the new equation phi of E, because to that entire charge, Q capital, that's why I put inside over epsilon naught. Remember in the last meeting, I told you that the charges inside the closed system is different from the charges outside the closed system. The first difference is the influence of other parameters of variable on external charge. External charge cannot be unidirectional. That is, you have to consider the direction. But else, the charge within is only limited by the radius of the circle. So that's why R is important in our general equation we arrived at in our last meeting. So for now, take that the flux inside a closed system, because of the ratio of the entire charge and the epsilon naught. So epsilon naught will be given to you in the exam. So the other two, they find either phi of E or Q capital. And equally, you should be able to make the Q capital the subject of the expression from this equation. That gives you a better understanding. Now, the electric field inside a uniform charged spherical shell is 0. That's another key point. And that will be illustrated by the diagram below. That the electric field inside a uniform charged spherical cell is 0. Now, if you look at the diagram, your A is not the same thing as B. What is the difference? There is an inscribed circle. Inscribed circle simply means a circle within a circle. So they can't have the same radius. Once the thickness of that circle is not the same, and the only condition for it to be the same is that there will be a layer over the other with the same radius. So that means no one is bigger than the other. So the radius with, the circle with radius small letter A is smaller compared to the circle with radius B small letter. So easily you can define the differences. And if you look at the Gaussian surface, which is the next figure, it identifies 3 circles. With these 3 circles, it indicates that we have 3 radii. R for the smallest, A for the next radius, and B small letter for the last radius, which is the biggest. So it's easier for me to find the charges within the regions of each circle. So the surface where the charges are operating is very important to Gaussian. So from his idea, we're able to discover that the field of motion, we're not talking about ordinary field, we're talking about electric field. The field of motion, once it's within the region and not outside the surface, you have the rule of the equation given to you earlier, that this must follow that Q over epsilon naught. That would be the flux. And you can see the plus around the circle. It makes meaning. Because electron is very important to us when we are discussing charge. In fact, the only difference is the symbol of negativity and positivity. So that's why electron is still charge Q from your simple knowledge. Now, from this level of understanding, we can further explain that electron has a free motion. And so when any object or particles has freedom of motion, then you can only define the speed, you can't define the direction. So the direction can change because angle can change at any time. That will lead you to the next idea of the diagram. Now look at this diagram. To make you understand it, that's why it's a bit expands beyond the level of the previous one. Now I have changed the letter. You can see the radius small letter r indicating the dimension, which is half of the diameter for the biggest radius among the three. So the next one will be small letter A, representing the radius of the smallest circle within the inscribed circle. So if you are to number these circles, there are how many? So that's a question to you. Okay. So you can count about 1, 2, and 3. How do you identify it? Because of the number of radius. Each circle has its own radius, but that is to redefine the motion of electron. So in this case, when the particles is charged and it begins to move, then you have the idea of negative motion, positive motion. All the motion, either positive or negative, is talking about direction. So the minus there does not indicate the value. When I put minus, it means I'm talking about direction in the motion of charges. It's just like what you have been taught on collision. Collision is a topic in physics, and part of it is also in mathematics. So when an object moves in the opposite direction, it's different from when the same object moves along the same direction with another object. So in that case, the direction will indicate positivity or negativity. Also, when the two bodies are now moving together, you subtract the differences. But when they are moving at different directions, what do? You add the difference. So that gives you the distance between the particles, between the two electrons, or between the two charges. So take note of this explanation because you will need it in the exam and in your test. Direction of the charges is good, but it's not as important as the quantity or the value of the charge by which you want to consider. So we can now move to the next subtopic. Electric charges, force and field. There are some statements that must be noted here that the study of electric charges is referred to as electrostatics. So in other words, this is leading us to the next subtopic. The word electrostatics combines two things. We are trying to redefine electron motion when it's at the point. So the word statics is not talking about dynamics. So the other opposite word, the dynamics. If something is not statics, it means it's dynamics. That is, it's a motion. And so whatever is statics, take note. What will you say about the distance? So whatever happens when an object is in motion is suggesting to you that it must have speed, or at least the velocity in a new version of unit. But when an object is static, not moving, the velocity will be what? 0. And so most of the introduction we are making here is not to totally remove or nullify velocity, but to tell you that the electrostatic motion is not so related to speed. And so we now discuss the static electricity, therefore, itself. The static electricity, therefore, is the studying of electrical effects produced in which lightning-like effect is seen when two bodies are rubbed against each other. Now, take note of that again. That is when we are now considering static electricity. We are studying the electrical effect produced when any lightning strike effect is seen, that is observed, when you bring two bodies together and you rub them against each other. So rubbing two bodies together brings you to a new discussion. What is the nature of the body you are bringing together? How come that is charged when you rub it against each other? The next question in mind is, what is the property of those two bodies? So property identify the nature of a matter. And of course, I want to assume that everybody understands the definition of matter. So in this case, it is easier for me to explain that when you bring two bodies together and all of a sudden it exercise or give light all of a sudden, or a crack, you can take your dry towel at times or dry comb, as we are taught in the O level. Dry comb and dry hair. When you are combing your hair, I mean grown-up hair, and hair is dry without water, and you have comb that's made of plastic. Combing your hair creates a crack. That this charge is initiated. So this charge is important to us as science, because it can be interpreted in another way to establish there is an electron. The electron in this case is not dynamic, but what? Statics. And so that's we now say this is electrostatics. So that this electrostatic does not mean it cannot create charges. So this is where your charges links with the electrostatics principle. So thus, studying of electrical charges is known as electrostatics. So anytime you want to discuss charges, but in electrical form, right now they're talking about electrostatics. Because you are not connecting wires before you see the influence of ions. Ions, in this case, I mean IONS. So very, very important. Now let's look at microscopic view of charges. And this idea was brought for the first time by J.J. Thomson in 1890. So meaning that he believes that electric charges exist in the atom itself. So I can ask you a question on this particular topic, and I can put it in any way that you understand better. Because this time around, I want to believe that I don't want anybody to fail this course. So you have to work harder and be sure that you read all these things repeatedly. So any atom that you come across, this topic assumes that everybody understands what we mean by atom. But you have done it in secondary school, even from DS school, from good school anyway. Electric charges exist in the atom itself. So if you are asked, where can charges, electric charges be found? So you must know that atom is one of the where in which the electric charge can be discovered. Then two, that all materials contain light. So light is what? Negative charge particles, which we call electron. That's what I said the other time, that the difference between what we call proton and electron is the direction of motion and the charge involved. One is negative and the other one is positive. So when the two comes together, they create a neutral ground for electron to move or for charge to flow. And that charge can be in form of electrical or electrostatics. So when it's electrical, it becomes what we call current electricity. So because it's moving, you are seeing it, and it is charged and it's induced also. These are the property of current electricity. Now back to what you are saying. So J.J. Thomson discovered that all materials, all inclusive anyway, contain light. That the light is indicative or not indicative does not matter. But when the property manifests or materializes, it means it contains light. So it's not every light that glows. That's what he's saying. The next point, atoms have a massive positively charged nucleus. And I can ask you who said that. That is Rutherford. Rutherford is the first scientist who discovered that atoms have massive positively charged nucleus. So nucleus is important when it comes to the study of charges. Then the next point, it is the electron that surrounds the nucleus. It is the electron that surrounds the nucleus. So you have to be mindful of that. Electron actually surrounds the nucleus. The next point, the positive charge is exactly balanced by the negative charge of the electron. These are properties you have to note, so that when one is missing in the option, you know that this one is the one that is missing, or this one is the one that is wrong. If I want to test now, I can say it is the electron that moves vertically to the nucleus. Is that correct? No. That's how to identify the wrong statement in the option. You should know the electron is the one that surrounds the nucleus. It is not the proton. It is not the neutron. So these are the three properties you're familiar with when it comes to matter nucleus. And that the positive charge is exactly balanced by the negative charge of the electron. That's why it becomes a complete atom. Next point, material that allow charges or electron to move about so easily are electrical conductor. Can you see the definition coming out now? That is, any material that allow charges or electron, meaning that we have taken into consideration the meaning of the two, so that when I represent in any equation that your Q small letter is equal to E, and I give you the value, is still the same. So when I interchange charges for electron, we are still working along the same line of correction. So any material you come across that allow charges for electron to move about so easily are referred to as electrical conductor. So whatever is called electrical conductor has the following properties of implication. Number one, it will allow charges to flow. That's why it's conductive. That means from one end to the other, no matter how long it may be, once it's a conductor, electron will flow through. And when electron flows through, the quantity of charge determines how dangerous it is to move closer or nearer. Because your body is also conductive. Yes, your body is conductive, and so unless you put on an insulator, then you have to be careful of any material that allows charges around you. So if I were to be in the class with all of you, I would have given you a simple demonstration. Usually what you do is to allow the student to touch each other and explain what you have experienced. Somebody will say, the moment I touch him, I discover the temperature differs. Is that one is zone or our one is hotter or colder? So how do you know there's a direct conduction? And the common example you have been familiar with, the one you are taught in secondary school. You take a teaspoon and dip the first end of the teaspoon in hot water and wait for some minutes and touch the other hand. Because that teaspoon is a conductor, it will have conducted the heat from the other hand to the last hand where you are touching or holding. Telling you that it's also transferable even to your body. So any system that easily allows charges or electrons to move is electrical conductor. So take note of that. You should be able to explain that. Now this presents the diagram as it is. I'm just trying to illustrate with diagram particles with the same sign of electrical charge. What happens to it? Particle with different signs, what happens to it? If you look at the first figure, something is clear about this figure. The first thing to know is that the direction of the suspension, the vertical suspension of the material by the thread or by any hanging object, show how vertical it is. Number two is the arrow, which is painted in green, is to illustrate the direction. And so, two directional way. We used to talk about clockwise moment and the anti-clockwise moment. And so two glass objects, and that's why the material is also important when you are talking about charges. These objects are made of glass. And so glass is considered to carry now this positive charge. And so when you bring these two glasses together, look at the direction of the force from the diagram also, very, very important. The direction of the force must be considered in the application of motion. So because force defines motion. When you apply a force specifically to objects, you are expecting the object to move. Then the movement must be in the direction of the motion. Take note of that. But when you apply a force and the body remains, it means you have to look at other forces involved. And that's why the word statics is also in line with forces. So there's a force holding that object to remain at position. That's what they are saying. Once the force causes the body to move, then acceleration is now used as a word to explain motion because the body accelerates. So that's why at any time, acceleration is one of the factor quantity. Because you are not just talking about the size or magnitude of the acceleration, but you are talking about the direction of the motion. So motion is important here when it comes to charges manifesting within particles. Now the next figure. The first one is glass, but take note of this green color. The green color indicates the anti-clockwise motion. Opposite of clockwise, that is, just like the hand of your clock moves. When your clocks move in the normal way, then you call it clockwise. But when it's opposite the other way, it becomes anti-clockwise. So bringing glass in contact with plastic, because these two are charged bodies, they allow charges to move, to be embedded in them, either positive or negative. Once they are charge carriers, they either attract or repel. Now, the second figure, I'm bringing glass and base plastic. And what do you notice here in this figure? There's an attraction. So the attraction now can be described as force of attraction. There is another force that causes the other object in figure A to repel or separate. So this you must be mindful. The forces are involved for any object to move towards each other or away from each other. That's the summary of what you are saying. And when two forces come together and they coalesce, what does that mean? Join together, then they have common velocity, just as you have been taught in collision. So, in other words, collision cannot be possible until the objects are in opposite charge. One will be negative, one will be positive. But collision will not take place if they have the same charges. That is, the two are positive or the two are negative. So they will repel each other. So that brings you to the former idea of statement that the same sign of electrical charge repel each other. And particles with opposite signs attract each other. So I want to say, assume that you understand this so clearly. All right? So evidently, I want to see if there's any comments or questions on what you have been doing so far. And like I told you in the last meeting, this class is very important. That will show whether you are really following or not. So mind you, take note and be available for these classes. It's easier for everyone to pass once you take note of simple instruction from the classes. Not only this class, other classes are equally important. Okay. Good. Yes, I can see your response. So we can go back. Now we'll move to the next slide. If you look at this diagram, it's a bit different from what we have just discussed. The first figure A, you can see the forces push the particle apart. We are just looking at positive and positive material being brought together. Now look at the direction being indicated and explained with the diagram. B diagram shows the same thing because the property of the first material is negative. The property of the second material is also negative. You can see the way the arrows are separated. That's to explain the like charges and the relationship between the two of them or more. Now the C figure, figure C, explain the forces that pull the particles together. Now we are seeing another particle of different property. One is positive, the other one has negative properties. So in this case, it's easier to see that the two will eventually come together or they are attracted. So the forces that bring these two objects together will be explained better or studied better in another topic. Because forces is a lot in physics. It combines so many topics, particularly when it comes to relationship of particles, not just a single object. The particles are multifaceted. We are not talking about size now because size will bring us into another principle. But just assume particles of the same size are brought together, and so there may be more in thousands. So that gives you the idea of what they call collisions. When the space of the particles are far to each other, the rate of collision is minimal. So the charges involved will also be what? But they are not in contact. But when you have two or more particles so close, the charge is influenced. And so the density of particles, therefore, by the principle of this theory, density of particles has a lot to do with concentration, with collisions, and with energy exchange. So in case a question along that line comes up, we can't write everything in words, but these are bullets for you to understand. That's why I'm taking my time to explain that the principle must be equally clearly understood. As I'm about to round up, because of the assignment, I want us to start this new topic. This new topic is called Coulomb's law. Coulomb's law. So, for Coulomb's law, it is easier for us from what we have been discussing on the principle of charges. And two, I want to assume that Coulomb's law is not new. You must have come across it in your O-level classes. Let's go directly to the definition. Simply, a Coulomb is defined as the amount of charge that flows through any cross-section of a wire in 1 second if there is a steady current of 1 ampere in the wire. Indirectly, by your simple understanding, we are trying to bring out equations. And the more the equation, the happier you become, because equations defines what you are trying to explain better. So it's easier, as we have said earlier, to see capital letter Q as our charge. I capital will now represent your current, and T small letter represent the time. And mind you, every specific topic, or even word in mathematical or physics, will have its own symbol and unit. So electrical charge is measured in Coulomb. So Coulomb is the name of another scientist we are going to explain later, just for your enjoyment. But therefore, you must be able to understand the general statement, which is now agreed upon as Coulomb's law. So Coulomb's law states that the magnitude of the electrical force, now represented with capital letter F, exerted by 1 point charge on another point charge, is directly proportional to the magnitude of the charge represented by Q1 and Q2 of the charges, and also inversely proportional to the square of the distance r. So this part of the study, assume that you are familiar with one topic in mathematics. They call it variation. Variation links two or more properties together to relate them and make it uniform. So when you say A varies as B, so if you want to say A is equal to B, then you have to put a constant. So now we are looking at 3 properties here together. The first one is the force. The second are the charges. if it is more than 1. Then the third one is the distance between the charges, which is now represented with R. Another person can decide to pick another alphabet. But for me, and for now, and for the general idea of a science, we are using R. So that's to introduce this topic to you. And finally, on this point, you can now put it together as equation. And that's the equation you are seeing now, that F, you can see that arrow on F, it makes meaning to us as scientists. That means F, as you see there, is a vector quantity. And it has a defined direction. F, therefore, is K Q1, Q2 over R squared. So take note of that. Q1 represents your first charge. Q2 represents your second charge. R small letter is the distance between the charges. And sometimes, 3 things to explain here before we go. If the charges are equal, that is Q1 is equal to Q2 in your question, either in test or exam. Sometimes there are some questions we're going to be tested with in electron properties. So you just square the Q. So the equation cannot change. So don't be surprised when Q1 is equal to Q2, and you are saying Q1 multiplied by Q2, that's Q squared. So when you now come across another equation stating that F is equal to K Q squared over R squared, it is assumed that that Q1 is equal to Q2. Okay? The last diagram there represents 2 charges with distance R small letter apart. Q1, the first charge, Q2, the second charge. And so the positivity of the charge, of the 2 charges, shows what? They will move apart, but they don't have the same properties. And so they repel each other. That is already clear from the previous explanation. So it's easier for us to calculate the force, which is the connection between the 2 charges. So clear? So that quantity, K in the expression, and I've also explained epsilon naught here. Your K is 8.99 times 10 to the power 9 Newton meter squared per Coulomb square. Sometimes I can test you on unit like I've told you. So you should also note that K is equal to 1 all over 4 pi epsilon naught. So sometimes when K is given, it is easier you just substitute the value. But when epsilon naught is given from the value indicated above, 8.85 times 10 to the power minus 12 Coulomb square per Newton meter square. Then you make your substitution and solve the problem before you can get the final value for the force applied on the particle or on the object. So this should be a convenient place for me to stop. Now I want to wait to listen to your response and questions. Okay. Please below definitely. I don't know where you have put down your name, but I can understand your comment. Oyinlola Oyediran. Okay, good. You are saying thank you, sir. Okay. So next meeting, we're going to discuss further. Thank you.
I want to online this.
See? Good morning, everybody. It's my pleasure to welcome you to Physics 104. We'll continue where abruptly we stopped last class. We had issues with the power. So I will repeat the introduction by mentioning my name. I'm Professor Jegede. I'm your course lecturer for Physics 104, which is General Physics 4. In the last class, I was trying to explain that motions are of different types. We have linear motion, which we are accustomed to. We also have circular motions, and we have oscillatory motions, whereby the body moves back and forth. I showed slides of these types of motion last class. I will now come straight to the business of today, which is I want to talk about the kind of motion body that are attached to springs experience by virtue of extension or compression of the spring. If you look at the screen in front of you, the slide shows a representation of a spring. I'm putting the cursor on the spring. The one on the left shows the spring in its unstretched state that is depicted as I've pointed the cursor to. Now, the spring experiences some extension or deformation when there is a weight attached to the free end. The upper end is fixed, while the free end, there is weight, a weight attached. And by virtue of the gravitational force acting on the mass, there is some extension, as you can see in the middle diagram here, where the unstretched spring by the distension due to applied force causes it to elongate, and that elongation is shown by a displacement measured as length x, as you can see on the screen. It is the weight pulling on the string that brings about some extension. Now, that extending force acts on the spring as to cause some deformation, and that deformation makes the string to produce a corresponding force, which is called a restoring force, because it's been changed from its natural configuration to lengthen it, as shown,
by increase, and that is what is indicated, that that force, extending it, produces a restoring force on it proportional to the extension. Again, look at the diagram. We have a force producing a corresponding extension, and that extension suggests that there's a proportionality in that extension, which is brought about by the force. This is common sense. If you are pulling, the amount of effort or force applied gives a corresponding displacement, and this is referred to as Hooke's law. Hooke's law. Simply put together, the force is proportional to the extension. And if you increase the force to twice as much, as shown in the right panel here, the extension becomes twice. So correspondingly, as you increase the force, the extension increases. Now, I will show you that if you look at when you have an extension, this is another arrangement. In this case, I have the spring lying horizontally. As the spring lies horizontally attached to a mass, if there is no extension on the length of this spring, as shown in this left panel, once the spring retains its original configuration, that is, it is unstretched, then there is no restoring force acting on it. And in this configuration, the spring force is adduced to be equal to 0, because the spring is retained without any force acting on it. But if you come to the right panel, if you compare, we have applied some force to pull on the string, and that pull is indicated by an extension corresponding to a length x. Remember, in the previous panel, I'm talking about this panel, we have agreed that the extending force is proportional to displacement. So if I come to this case whereby we've subjected the spring to an extension by elongating its length, there appears a corresponding force, which is the restoring force. The restoring force from that earlier expression is equal to a constant multiplied by the extension. So from the left panel, if we move to the right panel, we can see that considerably the extension experienced by the spring corresponding to a displacement x can be calculated as the restoring force, which is equal to a constant multiplied by the extension. Immediately, you observe that there is a negative sign indicated. Why the negative sign appears is what I put bottom panel here, that the negative sign is indicative of what happens by extending the spring, produces a force called restoring force. And the manifestation of this force is such that it works in the opposite direction of the displacement. So I come again to this diagram. You will now see that by virtue of extension that's occurred, the restoring force appears, and since the restoring force is opposite to the applied force, that points to the left side. So when the spring experiences an extension by the pull, the spring reacts by producing a restoring force that's as indicated. So in the second panel here, you can see that the restoring force points to the left because of the extension which is being experienced on the spring. So the restoring force always acts opposite to the extension or displacement. And that is the reason why a negative sign is indicated. So negative sign shows that the restoring force, which is proportional to extension, but acts opposite to the direction that the displacement occurs. So we take this expression that F equals minus the spring constant K and displacement. That is the statement of Hooke's law. Now, I just want to make obvious. Suppose instead of an extension on the spring, we are now looking at a compression. If we are looking at a compression, in this case, what happens is that from the original state of the stretched spring, there is an applied force applied to push to the left side. Thereby, as you can see in this second panel, we have experienced now the spring shows a reduction in length, that is subcompression, by applying force to the left. And when that happens, if you look at this orientation well, the displacement moves to the left towards the negative x-axis, and decrease in length is indicative of compression. And in this case, the spring tries to react by counteracting. The spring tries to counteract the compression by producing a restoring force like it did the other time, but this time around, the restoring force is not to the left, it happens to the right. The reason is that it tries to regain where it was originally. And in that case, we still have the same expression, but the direction of the restoring force is to the right on the screen. So these two cases, when you have a compression and an extension, again, I flip back so that you can see what I'm talking about. In this first consideration, we're looking at a force that is pulling to the right, which thereby the spring experiences an extension, and correspondingly, that extension brings about a restoring force that points to the left side. So compression, a reverse, we have the restoring force given by Hooke's law statement, and the force acts to the right side. Now, we are talking of forces on spring. So we can now see how motion brought about by applying forces on spring can be related using Hooke's law, which I've just introduced. We are linking Hooke's law to motion, which is Newton's second law. As you can see, Newton's second law, which I believe we are all familiar with, and motion is proportional to the applied force. So the weight is another expression of force acting on objects or bodies. It's a force. Weight is a force. So if we now link Hooke's law to weight and motion, remember, Hooke's law is just a product of the spring constant and displacement. And if we want to equate forces impressed on a spring, which I will show shortly, we can now determine that